Hi, this is Tom Buffano. I'm going to talk to you today about modeling your EK210 design projects. I'll give you some ideas, some hints, and some suggestions. If you have any questions or need any clarification, you can email me. I'm going to talk about all 6 projects, and I'm going to talk for each project about what I think some relevant modeling questions might be, and I'll talk to you about hints for that particular modeling question. And then finally, I'll suggest some preliminary projects or feasibility projects that you can do to test aspects of a model for your design. First project I'm going to talk about is the solar-powered water distiller. And the modeling for this project involves understanding the energy associated with vaporizing water. To vaporize water, you can use 2 techniques, either evaporation or boiling. Modeling questions are, what is the difference between evaporation and boiling? How much energy is required to heat water from room temperature to boiling? What area of solar collection is required to achieve what you need, which is to vaporize 2 liters of water in 8 hours, given a reasonable assumptions about efficiency? What factors are important in determining the evaporation rate? How does that rate vary with exposed surface area, ambient temperature, and relative humidity? So here's some hints on how to model the solar-powered water distiller. Both evaporation and boiling are techniques of vaporization, but one occurs only at an air-liquid interface, and the other occurs over the whole volume of the liquid, but only after it reaches the vaporization temperature. A reasonable estimate of light power from the sun in Boston is about 1,000 watts per meter squared. Another thing to keep in mind is that 1 cc of water has to absorb about 4 joules of energy to increase in temperature by 1 degree C. A third modeling hint is that evaporation rate increases strongly with the surface area of exposed water and the temperature of the surrounding environment. It also depends on relative humidity. Moisture surrounding air reduces the evaporation rate. You'll find that there's not an exact model for evaporation. One interesting problem that you can work on to get a quick model of the relevant physics is you can observe evaporation rate of liquid water with a given air-water surface interface area, and you could do that at several temperatures. You could estimate the evaporation rate in mass, and then consequently in volume, of that water. How much time would be required to evaporate 2 liters? What's shown in the picture is a setup where there's a dish of water at a certain temperature, at a certain humidity, and we're monitoring the rate at which that water evaporates, measuring the reduction in weight, and then we can convert that into a volume of water. And so you can figure out, will evaporation work for you as a model for this design problem? The next project we're going to talk about is the water pressure measurement and control project. And here, the modeling involves understanding water pressure measurement and pipe flow. Some relevant modeling questions are, suppose the inlet pressure to a 25 millimeter diameter piping system is 400 kilopascals. What's the pressure at a leaky outlet 1 meter downstream? For this example, let's assume that the leak is 1 liter per minute. That may not be what your client is interested in, but that's the one we're going to talk about right now. Does this pressure drop depend on the length and/or diameter of the pipe? How does a piping pressure sensor work? What range and sensitivity or resolution do you need for your design? So here's some hints. The Bernoulli principle. In a horizontal pipe, the sum of potential energy and kinetic energy is constant. Potential energy is pressure, and kinetic energy is 1/2 the density times the velocity squared. What is the volume flow rate of the leak, and how is that related to velocity? So what you know is that Before the leak happened, there was a pressure and there was no velocity. And after the leak happens, there's a different pressure and there's a little bit of velocity in the pipe. So you can, by knowing that the pressure and 1/2 rho v squared is constant, that sum is constant, you can evaluate the pressure drop knowing the flow rate. Generally, sensors tend to have a resolution that is proportional to range. So if you want your pressure sensor to measure a small pressure difference precisely, it's best to get a gauge that measures differentially. In that case, the range is the differential pressure between one point and another, and that might be very small. A quick model of relevant physics: find a pressure sensor and then measure the pressure drop across a liquid-filled tube at an inlet pressure of 400 kilopascals with a silent leak at the output. Plot the pressure difference versus the leak rate. What is your range and resolution? The next project is a human-powered recharger, and the modeling for this project involves conversion of mechanical power into electrical power. Usually this involves a generator of some kind. Modeling questions are: for a generator that's charging a battery, what does the equivalent circuit look like? How do the output voltage and current from the generator vary with its rotational speed? What circuit elements could you use to prevent you from overcharging a battery attached to the generator? What's the mechanical power to the generator in terms of resisting torque and rotational speed? What is the electrical power from the generator for a given battery voltage and charging current? And what's the efficiency of the conversion from mechanical to electrical power with respect to electrical and mechanical power? Here's some hints. A generator produces a voltage, and it's often called the back electromotive force, or back EMF. And that voltage increases with the rate of rotation of the generator shaft. The generator voltage is connected to a fixed voltage battery through a resistive load. And usually that resistor is on the order of the same resistance as that across the leads of the generator. The mechanical power is torque times rotational speed. Electrical power is current times voltage. So for a generator, the torque required, or the torque that's driving the generator, is proportional to the current that it delivers to the load, in your case, a battery. So here's a quick model of the relevant physics. Find a DC motor or a generator and use it to drive a resistive load by turning the shaft of the generator. Measure the output voltage and resistance as a function of the generator's rotational speed. How much power can you get from the generator for different operating conditions? Next project is the lamp post mounted flood detector. And modeling for this project involves understanding two things: water level sensors and remote communication systems. So some relevant modeling questions are: what are the physical properties that differentiate air, which is the normal surroundings of your sensor or detector, and water, which is the flood condition surroundings of your sensor or detector? How can those physical properties be exploited to devise a sensor? And what is the resolution, range, and operational bandwidth, meaning measurements per second, that's required for your depth sensor? Can relaxing requirements for one of those variables in your depth sensor make the other ones easier to achieve? What are the trade-offs in communication systems operating in low-power environments? What's the relative energy cost associated with distance, data rate, and the amount of data to be sent? Are there models that can help evaluate these trade-offs for this application? Here's some hints and starting points. Measure the electrical resistance between two conductors immersed in tap water. How does that resistance change with the spacing between your probe's conductors? Generally, the power required to transmit information to a remote receiver increases non-linearly with the distance to the receiver. Power is also increased with a required communication bandwidth. If you want to send data faster, it takes more power to do so. So here's a quick model of the relevant physics for this problem. By now, you've picked a means to measure water level. Make a quick and dirty prototype of just that sensor and determine its repeatability, range, and resolution. Will it work for you? If not, modify. Next project is detecting toxic substances. And the modeling for this project involves understanding rapid thermal control systems and the relationship between heat input and temperature rise. Modeling questions that might be relevant include, what's the ability of your device to absorb heat, and how will its temperature rise with a given heat flux? And what properties and geometries affect a material's ability to conduct heat or to insulate from heat? What properties allow the largest change in temperature in a material for a given heat flux? And what properties regulate the speed at which temperature rises that are due to heat get distributed through a material? Here's some hints. The heat capacity is a material property that relates thermal energy input to temperature rise in a material. Specifically, the energy input is equal to the mass of the material times its specific heat, Cp, times the difference in the initial temperature and the final temperature. The thermal energy getting to the material that's to be heated depends on the heat conduction of any layers that are between the heat source and the object being heated, and that's not captured in the model above. The cumulative heat energy is the power produced by the heater times the time that the heater is on. So here's a quick model of the relevant physics for this project. Pick a sample chamber and a resistive heat source. It doesn't have to be the final design choices for you, just pick one. Measure the chamber's internal temperature as a function of time with constant heat input power. What does the temperature curve look like and why? Using this data, determine what heat input would be required to get that chamber to the target temperature in the target time. The next project is the Kangaroo Care Transporting Incubator, and modeling for this project involves understanding thermal control and integration of sensors in a flexible structure. The modeling questions are, given that the incubator thermal system includes a parent producing heat, a constant temperature infant, and heat flux to cold surroundings through the incubator material, what is a reasonable estimate of the energy balance on a trip outside in Boston in December? What's the recommended dosage of bilirubin light and at what wavelength? What's the maximum allowable concentration of light to avoid damaging the infant's skin? Should lights be distributed or concentrated? So here's some hints. If the loss of heat is proportional to surface area and the required heat is proportional to body volume, answer the question, why are babies more susceptible to chills than adults? Think about it in this way. Assume adults and infants are proportionally shaped cylinders. They have a diameter and they have a length. And the baby diameter is proportionally smaller than the adult diameter, and the baby length is proportionally smaller than the adult length. If you do the math, what you'll find is that the surface area to volume ratio of the baby is much larger than the surface area to volume of the adult. And that scales with size. And so the baby is more likely to lose heat through that surface area in proportion to its body volume. Heat conduction through a material depends on the material's thermal conductivity and geometry, and that can be captured in this equation. The heat is equal to a material property, the thermal conductivity, times the area of the interface between that material and the inside and the outside, divided by the length or the thickness of the wall between the inside and the outside. If the parent and child have equal skin temperatures, what do you think the heat transfer will be between their skin-to-skin contact interface? One way to think about that is that the temperature of the parent and the temperature of the child are the same. So if you look at the equation just above, that means the heat transfer is nothing, is zero. So while the kangaroo care transporting incubator is preventing the baby from losing heat through the parent, it's also not gaining heat from the parent. Nevertheless, the infant might be losing heat to the outside. So here's an interesting quick model of the relevant physics. Fill a water balloon, which will take the place of your baby, with room temperature water. Room temperature water, you know what its thermal conductivity is and you know what its heat capacity is. Put that balloon in a refrigerator for 1 hour and then measure the water temperature. From the heat capacity equation, which was presented in a previous slide, you can figure out what the temperature change should have been for the water balloon. Construct a model that explains these results, and then refill the balloon with room temperature water, wrap it in a candidate incubator material, and repeat the experiment. Now you have heat loss through the insulator, and you can use the equation that's on this slide. Can you determine K from this experiment? These simple examples of models and hints and ideas about how you might model your design are intended to inspire you to think about modeling for your project, but they're not prescriptive. You don't have to do the models that I prescribed, and you don't have to model the areas of your project that I thought were interesting to model. Your project is your project. You can decide to model whatever you think is the most important physics associated with your design. I appreciate your attention. Good luck in your modeling.